Hello, and welcome to this ASM webinar series on the Materials Platform for Data Science, or MPDS for short. This success story on high temperature oxidation of Inconel 625 is the first of many success stories that we will be highlighting in the MPDS webinar series. So make sure to keep an eye out for more. I will get to a little bit more about myself and today's speaker, but I do want to welcome our guests that will be joining us for the Q&A portion of today's webinar. Dr. Afina Lupulescu, Senior Product Developer at ASM, and Dr. Evgeny Blokin, founder of Tilde Materials Informatics, that amongst other things maintains the platform that MPDS is housed on. ASM International is the world's largest and foremost professional technical society serving the information needs of scientists, engineers, and technicians who develop, test, select, and apply advanced materials, including metals, composites, polymers, and ceramics. As the world's largest and most established materials information society, ASM engages and connects members to a global network of peers and provides access to trusted materials information through reference content and data, education courses, international events, and applied research. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulty in joining the GoToWebinar session, dial 877-582-7011. All participants will be in listen-only mode during this presentation. But don't worry, feel free to submit written questions at any time by using the Q&A window located in the lower right corner of your screen. Click the question mark button to open a Q&A window, type your question in the box at the bottom, and click the send button. We'll answer as many questions as we can at the end of the webinar. Now, I am Nate Bullcroft, BDM here at ASM, and I focus on growing our corporate relationships. I am the main point of contact for MPDS here at the Dome, but I'm also responsible for growing our corporate memberships, digital library, and expanding our comprehensive content footprint. I encourage everyone to reach out to me utilizing the contact information listed on the slide. And I'm truly pleased to be joined with today's speaker and ASM's Executive Director of Product Development, Dr. Ray Fryan. Ray is leading cross-functional product development at ASM and also leading the team building ASM's digital data ecosystem product line that we will be bringing to market in the near future. Prior to Ray's employment at ASM, he was a longtime ASM member and treasurer of the Board of Trustees. Ray's professional industry experience includes over 37 years with the Timken Company and Timken Steel Corporation, where he most recently held the position of Vice President of Technology and Quality. Welcome, Ray.
Thanks for your kind introduction, Nate. It's a privilege to be part of the ASM International team, particularly in a time of great change, new strategies, new products, and delivering greater value to our membership. The ASM Materials Platform for Data Science, MPDS, is just the beginning of what will be a series of new things that ASM will be offering our members and stakeholders. So just what is ASM's MPDS? It is the digital continuation of the polling file, a compendium of critical inorganic materials information. As we thought about MPDS and how it fits into our portfolio of digital products, we concluded that it's a materials platform that will accelerate innovation at the intersection of material science and data science. MPDS is the world's largest and most comprehensive repository of inorganic materials data. These data include phase diagrams, crystal structures, and a broad range of properties: physical, mechanical, electrical, optical, and magnetic, to name a few. MPDS has a rich set of scientific publications underpinning these data and is perpetually growing thanks to the ongoing full-time work of the Polling File Project. MPDS also has a very intuitive graphical user interface, or GUI, that makes deep dives into the platform data convenient and straightforward. Lastly, because of its span and its scope, there's nothing like MPDS anywhere else in the world. Today's success story will focus on using MPDS through the graphical user interface, or GUI, in a problem-solving setting. In addition to the GUI, an application programming interface, or API, option is also available. This API will be exercised by ASM authorized experts to create custom data sets for the customer's use, often to feed machine learning or other simulation activities. This intersection between data science and material science is a critical underserved need for materials researchers trying to find new material functionality and to solve critical industry problems. It's also an area of explosive growth in materials research. Spoiler alert, this MPDS function will be featured in a future success story in our series of MPDS webinars. Let's talk about the foundation of the platform. MPDS is all about the data and accessing those data conveniently. It starts with expert curation of the sources of both experimental and calculated data for materials properties. Dr. Pierre Villars and the Polyfile team of experts have been refining these data for over 25 years, and some of the underlying sources date back to over 100 years ago. This information, after curation, is placed into the platform. The sheer numbers are incredible. Over 200,000 publications, over 70,000 phase diagrams, over 450,000 crystalline structures, and over 1 million property values. This is a strong foundation that is both deep and wide. Through the use of embedded intelligent tools, including machine learning and concise searching, it's possible to quickly get to a destination for information that you didn't even know you needed at the beginning of your search. We'll talk about that specifically in the use case. I've already mentioned the custom dataset option to feed advanced analytics. Lastly, this is not a static one-and-done product. Because the data are constantly being updated, MPDS creates evolving value and is offered only in a subscription format. That means all the information is available to our MPDS subscribers in all ways, always. ASM members represent the broadest range of professional roles of any technical society focused on materials. We took our best guess at how aligned MPDS is to the roles that exist in our membership. By the way, we welcome any feedback where our best guesses are off, so please help us refine this assessment. That said, our first cut shows a lot of green and some yellow, great indicators that MPDS will be helpful to a broad cross-section of our membership. It's our expectation that more of this grid will become green as our members experience what MPDS can do for them. Let's transition to our first use case, a success story in the high-temperature material space. We'll walk through this from the perspective of a very smart, talented female materials engineer working for a sophisticated, design-responsible engineering company that had a big problem. The company involved was in the power generation sector. They had problems with valves sticking in a steam turbine that caused unplanned, immediate outages. Not a good situation. As we walk through the success story, our engineer has a heavy burden on her shoulders. This is a big problem and it's urgent. Get the valve operating properly and get it done ASAP. Fortunately, MPDS has some features and some functions that will help her to lead the problem-solving team with speed and precision that they otherwise wouldn't have been able to deliver. The problem-solving approach she took is a classic linear approach. Start with define the problem and work through the steps until she and the team got to gathering the facts and developing the actions to implement the solution. The black arrows indicate that the process is linear. In reality, problem solving also has a bunch of non-linearity to it. When our engineer started the journey, she didn't know the specific solution, and this is how real problems get solved in the real world. We'll also emphasize that smart people are the key to problem solving, and that the MPDS platform helps problem solvers deal with the messiness of reality quickly and effectively. To make this use case a little easier to relate to, I'm going to use the metaphor of a journey. Most of us have used the GPS to get from where we are to where we want to go. And most navigation systems require a specific destination to be entered to get you there. What if you only have a hunch or don't have the specific address? Do you just start driving and hope you figure that out along the way? Hang with me on this metaphor for a little while longer. Let's say that having the phase diagram of the material in play is like knowing that the needed information is somewhere in Ohio. The problem is Getting to that needed information sooner or later requires having the street address, ideally sooner. How does she get to that address to get to the information of interest to develop the solution? I'll call this journey progressively finding the information of interest, or progressive discovery. She could try to knock on the door of all 11 million Ohioans, but I think she'll run out of time and money before she gets very far. She knows that she wants to get the information of interest, the street address, and that there are already search tools out there in the public domain that can give you lots of things to look at. The question is, how relevant are these search results, and how easy are these results to digest and make a good decision from on the next step? Most problem solving has an element of progressive discovery, where we get confronted with just how iterative the problem solving process really is. Searching for the information of interest with normal search tools has this challenge for sure. Our engineer may get some relevant search results in the upper left block buried in a bunch of highly irrelevant results. She'll put up with that situation only if she has to. Sometimes search results are highly irrelevant, and it doesn't matter whether those results are easy to digest or difficult. So the bottom two blocks are frankly a waste of her time, and she can't tolerate wasting her time. She's got a problem in front of her that is just too urgent. If she could have her preference, our engineer would like to have highly relevant search results in an easily digestible form, and ideally, not a huge number of them. Is there a better way? You already know that MPDS is the answer, right? Just for grins, our engineer knew that the chromium oxygen system was the metaphorical state in which a lot of her information of interest was located. So, the metaphorical street address is somewhere in Ohio. Using common search tools and 3 categories of MPDS information: phase diagrams, crystallographic properties, and crystal structures, she obtained search results in the millions. Kind of like trying to get every street address in Ohio. By comparison, MPDS provides an effective way to progressively find the information of interest, and do so without sorting through millions or even hundreds of mostly irrelevant search results. Starting with a huge collection of phase diagrams, she can quickly and iteratively get to the information of interest in a progressive but efficient fashion. In addition to this rich data foundation, MPDS presents that in a number of file and digital image formats that are both convenient and efficient for progressive discovery. Our engineer knows a fair bit about the context of the problem, including the incumbent alloy and phase diagrams she wants to review. She knows more about the alloy substrate that is oxidizing and less about the oxide film she believes is the culprit. She also knows something about the heat treatment surface options that are in play. She will supplement her experimental plan with the information contained in MPDS. It contains experimentally determined and CAFEB-based calculated phase diagrams, many of which were created using ThermCalc, a commercial phase calculation platform. All these resources will be brought to bear on the problem and will help her and her team move forward with the ultimate solutions they want. I mentioned that she knows more about the Inconel 625 substrate and less about the oxide layer that forms that is likely creating the sticking. Our engineer wisely refines her experimental approach to narrow the progressive discovery to better understanding that oxide layer that is forming. She has a lot of questions, and she frames the problem with some needed experimental information. What's in the oxide layer? What oxidation mechanism is in play? And does spalling occur? She wants to know about spalling to understand whether the oxide is adhering or not during service. She suspects that some spalling could actually help eliminate sticking in the operation of the valve. Our engineer was able to get samples of the Inconel 625 alloy and oxidize them at operating temperature, 1400 F, for a range of times. She then had the lab characterize the composition and thickness of the oxide layer and determined a few key issues. Chromium oxide, in this case Cr2O3, is the primary oxidation product, and unfortunately the thickness of the oxide increases following an exponential rate. Fortunately, the fact that spalling appears after 8,000 hours should help mitigate the valve sticking problem. Knowing this, she's progressing towards where the information of interest is located, the metaphorical street address. She continues her journey towards the information that will help her and the team produce a solution. Using the graphical user interface in MPDS, our engineer gets from the state to the specific street address in 3 major steps. Remember, we want a relatively small number of highly relevant search results as we progressively discover that address. If we have to back up and reassess, and the reality is we'll want to do so after a minimum amount of effort. Our engineer and her team are now in a position to leverage the resources at hand. ASM's MPDS platform. Our engineer starts with the easy-to-use search function. She types in phase diagram, chrome, oxygen, and binary into the search dialog box. And the outcome produced a list of 12 phase diagrams, and 5 of those contained the temperature range of interest. She then selected the 1995 diagram that covered 500 to 3500 C and found the areas where chrome, CR203, and CR304 high temperature phases are stable. CR23 stability at operating temperatures has about 40% chrome and 60% oxygen. She clicks on the visualize icon in the upper right, and the phase diagram regions are highlighted as she scans her cursor over the areas on the phase diagram. On the left, there are 5 options she has in the drill down of this oxide system. The PDF option contains all the details of the phase diagram, including its polling file identifier. The JSON file contains the graphical details of the phase diagram that can be exported. There are also image files of the phase diagram in PNG and CDF formats. And lastly, there's a BibTeX option for the supporting references. Our engineer selects the PDF option. She sees more pertinent information about the system. The phase diagram, its bibliographic details, the phases, and the crystal data associated with the system. In the crystal data, she notices the crystal structure entry and unit cell parameters for CR203. She's pretty certain that these data will be very helpful for the modeling expert on her team. She clicks on the structure entry for CR203. This takes her to a visualization of the trigonal unit cell structure of CR203, and the unit cell can be rotated any way the user wants. Pretty cool, eh? Our engineer, after thinking about unit cell parameters for the oxide, starts to think about what would enhance spalling. Crystallographic mismatch between the trigonal CR203 and the Inconel 625 substrate. This information is the metaphorical street address from which the solution would be developed. The engineer and materials modeler hypothesized that a degree of matching between the crystal structure of the oxide form to the base metal underneath could be modeled to predict crystallographic mismatch at the operating temperature of the valve. In short order, they came up with the right geometry and composition changes that allowed for spalling, helping eliminate some of the oxide as it formed. As I've said a few times, this problem was solved by smart people, using the right problem-solving approach and using the right information. Getting to that right information quickly was the MPDS value add. Back to our GPS metaphor. Our engineer had enough experimental information to know that she wanted more information about the chromium-oxygen system. She then dug into the phase diagram and related phase information that led her to look at the trigonal crystal data for CR203. She went from state to county to specific street address to get to the needed information of interest, and did so effectively and quickly. With this critical information, she and the materials modeler developed a model to target the optimum composition of Inconel 625 and also recommend geometry changes that significantly improve the valve operation. Definitely a successful outcome. In closing, I'll walk you through a brief recap of this use case for MPDS, covering the main steps that our engineer and her team used to get to a solution. By understanding the oxidation, kinetics, and growth rate, the engineer focused her modeling expert on manipulating the crystallographic matching of the alloy and oxide crystal unit cells. This required a design adjustment and a tweak of the Inconel alloy. MPDS played a key role in getting the specifics of the solution in 2 of the 3 major problem-solving steps, and the end result was the valve sticking problem was solved and costly outages were avoided. Without MPDS, getting the engineer to relevant materials data quickly and effectively, the solution would have taken much longer to find. Before I turn the session back over to our moderator, I want to re-emphasize that this success story intentionally highlighted the power of the Graphical User Interface, or GUI, for very targeted materials information searches, progressive discovery, if you will. That said, MPDS has many other uses and functions, and many of those will involve some kind of progressive discovery. This success story covered only a narrow cross-section of MPDS functionality, and future success stories will highlight different features and functions through which MPDS can deliver value. Okay. At this point, we're going to transition to our Q&A portion of the webinar. Please feel free to enter questions into the Q&A box. Before I do that, and as you're thinking about your questions, I have a couple of additional issues to cover very, very quickly. First is, I have an announcement that comes from our former ASM board president, Dave Furr. He is going to be launching a members-driven technical committee on data management and analytics. This committee will be instrumental in helping shape the future of the ASM data ecosystem and all ASM information resources, including our new MPDS platform. So please be looking for more information on this committee and how you can join it in the coming months. Next, I'd like to give a little bit more background on our panelists, Afina and Evgeny, who will be addressing the questions that you will have. Dr. Afina Lupulescu has been with ASM International after finishing her PhD at Rensselaer and after a successful career at RPI, Union College, and General Electric. She serves as a senior product developer here at ASM and leads the technical content of our database and digital materials data products. She's represented ASM in a number of international projects and is also focused on data sharing formats and data translation. She also has a strong background in phase equilibria and crystallography. Dr. Evgeny Blokin is the president of MPDS IO, an Estonian-based company affiliated with Pauling File Project, a global team of materials and data scientists that manage the Pauling File and keep it current, relevant, and continuously improving. Dr. Blokin received his doctorate in physical chemistry at the University of Stuttgart. Evgeny manages and continuously improves the GUI interface, the ab initio calculations, and embedded machine learning, enhancing the underlying Pauling File data. So thanks to both of you, Evgeny and Afina, for joining us. And finally, as a reminder, if you haven't done so already, please use the Q&A window to type in your question. So let's go ahead and get started with the first question from our audience. The first question reads, could you please elaborate on how MPDS can be used to mine the information from phase diagrams, such as does the JSON file for that read in quantitative information from a given phase diagram efficiently? A follow-on question to that is, could you also clarify on the availability of the API to subscribers? So Evgeny, I would like for you to please address this question coming from the audience. Thank you.
Yes, sure. We have pretty much JSON support for the phase diagrams. So I'll demonstrate you on a particular example right now. Let me make just a simple search of any phase diagram and show you the real example So let's have a look on that silver lantern phase diagram, for example, which you can see right now. And at the left, it's available to access the JSON data. And there, of course, all the machine-readable information is extracted. Well, basically, it is suited for the visualizations, so that the labels, you can see the positions of the labels, the particular equations describing the phase areas, and etc., etc. And of course, all these fields are exposed through the API, for example, for the data mining, so you can build your own, let's say, CalPath models, or you can make simulations using this data. So yes, my general answer would be that we expose the machine-readable information about the phases, the phase diagram in JSON, yes. And of course, we also provide the raster graphics in PNG format. So I click, you can see these nicely redrawn pictures with the phases denoted by color. Let's say here, for example, white stands for 2 phase regions, and blue would stay for 1 phase region. Here it is liquidus regions, and etc. Here you can see at the right bottom the small legend explanation. Yes, of course, it's possible through the API to get access to the mass data. So let's say, for example, you are interested in some specific chemical elements or combinations of elements, and you can retrieve the matching phase diagrams and further process them. So yes, that's the supported scenario, and we'll be happy to assist you on that, of course. Yes.
Okay. Excellent, excellent. I'm going to move to a slightly different theme here, but I think it really gets to the root of the success story. And Afina, if it's possible, I'd like you to maybe initiate your comments and answers to this. One of the related questions was there a special tailored composition to completely solve the problem? And then related to that, does the alloy Inconel 625 need a thermal barrier coating? And I think in this case, the context of it would be with regards to the corrosive nature of that service. So Afina, if you would please address that.
We worked with, as you know, Inconel 625 is a multi-component alloy and has different versions of it. At GE, we developed specific heat treatment for specific needs that we are looking at. And how could I say, we worked for 2 different cases. We worked for oxidation in air, and also we used a specific process developed by GE in terms of nitriding. GE and body coat is a little bit different than the diffusion process that Siemens developed. So GE developed this process long time ago, and it worked beautifully. Some people are saying nitriding is not the best way to go. But for that particular, project, we did testing, and we saw that the nitriding layer is not cracking because it was a very, very thin layer, and it was delaying the oxidation process.
Okay, thank you, Afina. Great question. This one really gets to be a bit more of a foundational question, and I think I would like to have Evgeny address this first, and then maybe some backup commentary, Afina, from you. And This is a hard question. I'm glad it was asked. How do you guarantee that the provided data is authentic and properties or diagrams are obtained in a scientifically correct way? In other words, this is getting at, if you will, the quality of the curation of the information in the polling file. So Jenny, if you would start the audience out with your answer to that.
Yes, sure. First of all, a couple of words about the polling file itself. So this is quite a long-living commercial project on the data curation. So it lives already for about 30 years. So I think that's kind of impressive, so that it's operational for several dozens of years already. And what does it do actually? The answer is that these people, this international team, they process the published literature. And of course, we all think that this preparation, this curation should be done by the publishers, yeah, by big names, we all know them, but actually they never did that. And this is the motivation behind the polling file project, to create the relational database based on the published materials science data. And of course, to evaluate the quality, you can always refer to the underlying source publications. So here at my screen, you can see that literally every data entry is associated with the particular publication, which is done, let's say, recently or not right recently. There are quite a lot of very rare Japanese journals, Soviet journals that were never online, and still these data sources were carefully processed by the international team of polling file. And all this is done manually, and of course with the assistance of data curation modules, programs that this team developed for themselves. And you can make sure in the data quality clicking at the reference, and of course seeing looking at the particular publication which was considered. So you see, for example, here this is in the case of chromium oxide. This is the article from Elsevier, so you can download it and make sure that all the values, all the information pieces, they extracted carefully, and we can make sure that looking at the summary, which is accessible, clicking at the bottom, and well, you can see that there are a lot of valuable information extracted, and all this information basically originates to the particular published articles in the last, let's say, 100 years. So the first articles that are covered by polling file project, they are dated in the beginning of the last century. So there is pretty much data set of the processed considered publications. Here at the main screen, you can see this. I highlight this. So there is almost 300,000 of considered material science publications. And all they are, starting from now, all they are searchable in a way that you can type chemical formula, combinations of elements, chemical properties, crystalline classes, materials classes, and etc. And you can deal with this information online, just like this, very simply and quickly. So this is the basic answer, so that of course you can make sure in the data quality either through the demo access, so that you can, let's say, download a couple of articles and compare, really, to make sure that the data taken out verbatim from the articles and keyboarded in the database manually. So that's basically my answer.
Okay, Athena, would you please add your view on curation and processes, maybe specific to phase diagrams, as an example?
Yes, of course. MPDS has a specific process of data evaluation, and there are almost 100 different evaluation standardization derived data program modules, and the evaluation is applied. I mean, these 100 modules are applied at 3 different levels: editor level, section editor level, and editor-in-chief level. The result of it is that from the entries, 5% are, the editors are discovering fundamental errors, and 50% of all entries get an editor comment, and 60% of the data sets require standardization. For those who are interested, and I'm pretty sure some of the audience is interested in that, our way of evaluating, Pierre and Tim way of evaluating is different than MSI evaluation, and I'm very familiar with MSI evaluation. That goes analog to Lendold-Bornstein kind of evaluation, and it takes into account all the published system related to all the published literature related to a specific system, binary, ternary, quaternary, and so on. But is, as you know, is a very exhaustive process. And although I like MSI data evaluation, will require a lot of time and will be very expensive, and in addition needs constantly yearly revision. So thinking that there are almost 100,000 chemical systems material information, that will be a long, long process. And therefore, Pierre and Tim had to make some business decision at the end, and they preferred to approach in a different way the numerous chemical systems material information. Hope this satisfies the audience, because it's a different way of evaluating that curation.
Okay, thank you, Athena. And I just add, we've had a number of conversations about curation, about the reliability and the thoroughness underpinning the polling file. And it's fair to say, particularly for those that will be doing some version of API extraction of the information in the polling file, no matter what the curation process is, let the modeler beware. In other words, every modeler needs to understand the underpinnings of the data that they're reading in, and then make sure that they know how they're using it and what conclusions users of their model will have and try to create as a result of that model. So this certainly applies in the subject matter of data and literature curation. So I'll just move on from that to another even more difficult question, and it's a great question because this is an ASM product. And the question is, if data is downloaded from the polling file and then subsequently used to develop an AI tool, how does ASM control use of this derivative data tool? So I'm going to put a little bit of interpretation on this, meaning if someone had a custom data set that was extracted from the polling file, which of course would require a custom data set commercial arrangement with ASM, then they use those data to create a machine learning model? And then would they have the rights to use their machine learning model? I think the answer to that is yes. What they would not have is rights to the underpinning data that created the model. So Evgeny, if you would care to comment on that, that's a hard question, and this is right in the nice gray boundary of what we like to call digital rights management. So please, if you could comment.
Yeah, understood. So first of all, of course, the articles, they are copyrighted. Yeah, they belong to these publishers that we all know, and we all consider them for writing the articles. And of course, polling file in this respect, it just rereads this data. Yes, so people, they are downloading these articles and they just read them, and then they manually keyboard all the data into the database. So in this sense, they create a lot of additional value on top of those published articles. And here is the answer. So the copyright belongs to the polling file team. And all this data, as soon as they are delivered verbatim, let's say through the API, and they are in consideration of the user, of course, we cannot allow the user to redistribute this data as soon as they are copyrighted. I mean, these downloaded verbatim scientific data. But as soon as the user creates some derivative data, he or she further develops these data, of course, then our users are free to do whatever they prefer. And this is quite logical. So only those portions of information which are related to the particular work, they can be copyrighted. But of course, the scientific facts, they cannot be copyrighted, right? And as soon as you operate with these scientific facts, you are free to go, of course. I think this answers your question.
Yeah. Yes. Thanks, Evgeny. And to be fair, I think as we stand up our data management technical committee, these are the kinds of issues that we are going to have to tackle, both from a good IT control perspective, as well as from a policy and terms and conditions perspective with regards to what commercial rights will our subscribers have as a result of subscribing to MPDS in the GUI version, as well as what digital data rights do they have when they use the API to create custom data sets for their own consumption. So it's not a super clear, super black and white subject at this point, and I appreciate your answers thus far. I'm going to switch back to the problem at hand and then direct this one to Athena. It's related to the problem being solved, and it may or may not have a direct connection to what we showed in the use case. But this question goes: what microstructural characteristics cause high strength of Inconel 625 at high temperature?
How could I answer to that? I don't want to infringe much of the IP aspects of that particular alloy and that particular heat treatment. Yeah, I will just give to the person interested the name of the patent that was published by GE. And they could go from there because we controlled the carbon content for a specific distribution of the phase in discussion.
Okay, thank you. And so I'm going to back up a little bit, and it's a little kind of tying together of several questions, but again would require a team answer from both Evgeny and Afina. If a subscriber is interested in the coefficient of thermal expansion data, and they want that for use in a machine learning that they would like, algorithm or model that they would like to develop, how do they go about doing that? So Evgeny, if you could talk about the major steps that folks would do in an API to create a custom data set. And then Afina, if you could comment on how one would go about applying machine learning to a data set that was created that way.
Yes, so we have already showcased some example of machine learning using the MPDS. So what exactly did we do? We extracted some sets of physical properties, among them also thermal expansion. Thermal expansion was there among them. And we extracted the corresponding crystalline structures. Yes, and you see these are the main types of the data in the MPDS, also including phase diagrams, of course. So we had, in the end of the day, we had the crystalline structures and the corresponding values of the thermal expansion. And we just took very simple random forest regression model, and statistically we trained this model to reproduce the values of thermal expansion based on the given crystalline structure. So that's it. You can see now that we can give any arbitrary crystalline structure, and we can predict the thermal expansion based on the arbitrary crystalline structure. Let me show you the particular example. We have a nice online application on that. So I will show you. So we paste here, let's say, for example, some structure in SIF format. Here it will be just gold, but of course you can paste whatever structure you like. And then our model will predict the set of physical properties that it was trained to statistically predict. Of course, pay attention that there is no physics here. There's just pure statistics. And what do? We hit predict, and we see that for this gold structure that we have given, we predicted some values and also the thermal expansion coefficient. So voila, we have it, we have predicted it. And of course, we used the file data sets related to crystalline structures and the particular property values. So that's it. We extracted these properties using the API. We trained the model, and then we were able to generate new results, which of course are physically sounding. So they are not precise. This is there are some disadvantages, of course, but we were also able to estimate the quality of the predictions, and the quality of predictions was acceptable. So you can see that it works, so to say. Yes.
Okay. Thanks, Evgeny. I'm going to jump to this next question. Somebody that just submitted it, and it's a really, really hard question, and I'll try to answer some of it. The first part of the question is, who is ASM's greatest competitor? And then the second part, implied in that, the connected part is, will there be an ultimate goal to unify all databases in one system, or is it possible that different platforms coexist in a symbiotic way? So who is our greatest competitor? I'm thinking back to our, I think it would have been our 2016 ASM board president, a guy by the name of Bill Frazier, who put together a really, really good way to see where ASM fits into the world of materials. And I would say we don't have a lot of direct competition with any of the other material societies, but I see that we have good collaboration, cooperation, if you will, some way of having a symbiotic relationship with whether it's MRS, TMS, AIST, and so forth. So I would say we're looking to find great collaborators and not great competitors, just because of the way we choose to cover the material space. So that's my story. I'm sticking to it. That's the way I see it. I think Bill's framework was very, very helpful for understanding ASM's somewhat unique space, where we are trying to help pull things that come in the realm of scientific discovery and make them engineering reality that ultimately gets commercialized. And that reflects the nature of the membership that ASM has. And it is a different composition of membership than, say, TMS or MRS. Great organizations, and we, I think we collaborate well. So the second piece of the question was, will the ultimate goal be to unify all databases in one system, or is it possible that different platforms coexist in a symbiotic way? I think it's maybe in some regards a bit of a rhetorical question. The more realistic response is different platforms do have to coexist and connect in some symbiotic fashion. If you will, things like talking about federated data structures, and then just even trying to categorize the kinds of questions that materials engineers and designers utilizing the materials properties that materials engineers create. The range of questions are so broad and so varied that to see one data structure and one schema in the materials realm service all purposes, all future questions, all major current questions is well, either it's a little unrealistic or it's a little bit too difficult for me to understand. So I certainly would welcome either Athena or Evgeny to comment on that one. That's a hard question. One system that takes care of all of it seems a little bit of a jump.
Yeah, but I think the initial question referred to the competitors for this product.
That's the original. You feel free to comment on that as well, please.
Yeah, as far as I see, our main competitor is MSI or MSIT. You know, they are located in Germany. I know them very well right now. They, you know, they are going with a new kind of team. I like very much, and I'm ASM, I like very much their way of evaluating the phase diagrams, because you know, they gather all the literature published, they discuss every continuous or dashed line in a phase diagram, and this is great. Again, I thought I clarified our way of analyzing the phase diagram is a little bit different. I think MSI, if MSI will, you know, unify with MPDS, this will be the greatest product of all. But I would like you to focus on what makes MPDS great. Polling file represents the legacy of all published literature for the past 100 years. This is huge. I don't think anybody else has that kind of approach. I think MPDS program excels also in terms of number of binary phase diagrams, in terms of machine learning implementation, ab initio implementation, and property values exceeding right now over 1 million, values. I think this is a very unique product, and no any product will fit all the interests. But if you take parts of the best parts of MPDS and the best parts of our competitor, I think you'll have the benefit of covering everything related to a phase diagram, crystallographic phases of interest, and the property as well. I'm part of ASM International, and we are promoting this product because we knew the value of it, and I know a lot of people are interested in what we offer.
Okay, thanks for that answer, Afina. Again, tough question. So thanks to the participant who asked it. We call them the way we see them, and we're being very, very straightforward with you. With that, I believe we have covered virtually all of the questions that have been submitted. And so what I'd like to do, even though we haven't completely run out the full 60 minutes, I think it's a good time to wrap up at this point. So we're going to do that. And with that, I want to express my sincere appreciation to Afina and Evgeny for fielding your excellent questions with equally excellent answers. If you have any further questions, whether they be technical or commercial in nature, please contact Nate Bullcroft with your inquiry. His contact information is provided on the slide on the screen right now. So again, thank you for your participation in today's webinar. And as we close, I hope you'll take a few moments to complete our exit survey that will help us continuously improve our webinars and also help us select the next use case to feature in our MPDS webinar series. Thanks for your interest and have a great day.